Welcome to Physics 2211, Lab 2, Motion of Falling Object by Blake Schwabe. The purpose of this lab is to examine an object falling somewhat slowly and the effect drag and gravity have on an object falling from rest. The principles used: Newton's second law, force equals mass times acceleration, with forces of gravity and drag acting in opposite directions. Also, there's the momentum principle, F equals delta P over delta T, which gives the idea of change of momentum over time, which is very used in this system. Knowing what we learned about objects falling in projected motions, it should be more smooth and will have less errors, whilst in the observed motion we'll have slight inaccuracies but give an overall better idea on how physics principles work within the real world. And here's this experiment setup. All you need is an open space, a single piece of paper, a ruler, and a phone. You can measure a height to exactly 1 meter without anything in the way. Set up your phone to get a recording of the paper falling. Start recording and then get ready to drop a piece of paper without any force. Then using your measurements in step 1, you drop the paper down to 1 meter height and then you stop your recording. You then graph your data in the tracker to show your observed motion of your paper. If you like an example of how this would go, this is me doing this experiment. And after cutting everything and making sure it fits, this is what I got for my model. Now you can see it's a bit wonky because there's always going to be a little bit of errors, but you can see it does have a bit of an acceleration and then it kind of levels out. We'll get to that as a reason why. And then here's the code. This is the starter code. I didn't change that much, but the minor changes is B is equal to 0 to represent just gravity and no drag. And then 0.031 to show drag or the magnitude of that. And then I put the time as 1.57 because it fit the time of the experiment I had. I then added force and drag components just using the formulas used. I then used F net in the velocity to get a more accurate version of velocity, and then I changed the ball dot position to be changed by the velocity to make the position actually more accurate. Now, this is the model of the program without a drag force. As you can see, gravity is able to be used throughout the entire thing without any time to stop it, and the position will change at a more rapid rate. Whereas, a model of a program of drag force, there's a little bit of change in the beginning. It's not as noticeable because of how light my paper was, but you can see that there is a graph that goes down at a little bit more constant at the end. But here are some similarities and differences between the models and kind of why. All the graphs start at the same point and will go for the same amount of time. They all experience gravity, the same gravity on those objects. The difference being, the model with drag force is closer to my original graph than the model without drag force, but it's not extremely close because of human errors. Now the models are smoother than my observed model that I tracked. The projected positions at the end of both models are greater than what was observed. Now there are a few reasons as to why this kind of happens. It mainly is errors, human errors. It could be blowing of air that could have happened within my apartment. There also could have been errors of putting in data into the tracker. Measurements may not have been precise enough. It may have not been exactly 1 meter that was dropped. It may have been like 0.94, 0.9 or something like that. Or there could be errors within the code itself that may give slight differences between the models of what would be more expected. But, with all that being said, what does this all kind of mean? Well, within the models that I've shown, you can see terminal velocity hit within the program with drag force, and not the gravity only model, because the forces need to cancel out in both the positive and the negative direction to make the velocity constant. F net equals 0, which means no acceleration. That's why in this program right here it is more of a straight line, and in my model it is more of a straight line because of terminal velocity. Now, what if you gave an initial velocity of the object downwards? What would happen? Well, there would be no change in the terminal velocity of that object, even if the object was going faster than its terminal velocity. It would actually slow down because of drag force back to its terminal velocity, because they want F net equal to 0 on this. So, that'd be how. Now, with all that being said, thank you all for watching. I hope you all enjoyed, and I hope this kind of gives you a little bit of laugh after watching so many videos. Hope you enjoy.